So welcome all of you to the third tutorial session of power electronics applications in power systems. Uh, Today we shall be discussing. So in the last tutorial session, we discussed about the uh, transmission line parameters and how to find out the sending end voltage and receiving end voltage, and also sending end current and receiving end current. We uh, we also learned the derivations of how we can find out the expressions for the voltages and currents. In today's tutorial session, we shall do some numerical problems on the active power and reactive power in the sending end, active and reactive power in the receiving end, and also if some intermediate point is given between the sending end and the receiving end, how we can find out the active power and reactive power. So I will not go into the derivations that you will anyway see in the lectures. I will just talk about the expressions so that before going to the numericals, we are familiar with the expressions. First of all, uh, when we will uh, when we will calculate the active power and reactive power, we will take the sending end voltage as reference because all of them are phasor quantities. You can take any of them as reference. There is no problem. You can also take receiving end as the reference. There is no problem at all. So if you take the sending end voltage as reference, then the phasor Vs will be Vs. This is the magnitude times 0 degree because this is the reference. So the its angle is 0 degree. And the receiving end voltage phasor, this will be VR, which is the magnitude, and the angle will be minus delta. So this delta, this is called the power angle. Okay, this is called the power angle. And usually the receiving end voltage is lags the sending end voltage. Because generally we know that power is transferred from leading side to the lagging side. So this voltage usually lags the sending end voltage. And these expressions we already saw in the last week. The sending end voltage in terms of sending end voltage in terms of receiving end voltage and receiving end current. And this is the expression of the receiving end voltage in terms of sending end voltage and sending end current. These expressions you will require when you will derive the expressions of active power and reactive power for derivation. And what is the apparent power? The apparent power is Vs phasor times, this is for sending end. This is for sending end. Is phasor, this is conjugate. Okay, this star denotes the conjugate. So this is the generalized expression for calculating apparent power. This is applicable everywhere. Whenever you have phasor quantities, the apparent power would be V times I conjugate. Okay, and it will have real part and also imaginary part. The real part we will call active power, the imaginary part we will call reactive power. So after derivation, so if you just replace the expressions, so in terms you can just Vs will be this Vs magnitude 0 degree, and Is you can express in terms of Vr and Vs, right? So from this equation you can replace Is, and you can also find out what will be Is conjugate. And if you simplify that expression, you will get this. The sending end power will be something like this: 3 VSVR in the numerator, and in the denominator ZC sine beta. This ZC we already know, this is called the characteristic impedance, and this beta is called the phase constant. All of these derivations were done assuming the line is lossless. Okay. So if you remember in the last uh, discussion, the original expression was instead of beta L, we wrote gamma L. So instead of beta L in the expression, we wrote gamma L. But here we are writing beta L because we are assuming the line is lossless. So when the line is lossless, gamma becomes J beta. That's why we are writing here beta L directly. After the simplification, you will find the sending end power PS like this. Remember, when there is 3 here, these VS and VR, they are phase voltages, not line to line voltages, they are phase voltages. And if you distribute root 3 and root 3 between VS and VR, then this VS becomes line to line voltage and VR also line to line. So now you don't need this 3. This is another expression. They are same only. You can use any of them to find out the active power. Similarly, for reactive power also, you will get one expression like this. Okay. And if you express them in terms of line to line voltage, then QS will be this. The 3 will vanish and all these voltages will be line to line quantities. Okay.
ତମେ ପ୍ଲାନ୍ ମାନେ 5G ମୋବାଇଲ କହିଲେ ବାପନେ ବୋଲି 5G ପ୍ଲାନ୍ ପକେଇନେ ଚାଲିବ 5G ଭଳିଆ ଇଏ ଗଲା ପ୍ଲାନ୍ କଣ କରିବ 5G ସିମ୍ ହେବ ପ୍ଲାନ୍ ନୁହେଁ କଣ ସିମ୍ ପକେଇବ ସିମ୍ ତ ନାହିଁ ସେ ସିମ୍ ଚାଲିବ ନା ଚାଲିବ ନା ଯୋଉଠି ନେଟୱାର୍କ ଅଛି 5G ଅଛି 5G ଆସିବ
Excuse me, can you please mute yourselves?
ସିମ୍ ଫୋନ ଚାଲିବ ସିମ୍ ଦରକାର 5G ମୋ ସନ୍ଦେହ ମୋତେ ଥିଲା 12 ଥିଲା ଖର୍ଚ୍ଚ ନା ମୁଁ ସକାଳ 12 ଥିଲା ଆମର ଯିବ ନା ସେଠି କଣ ଅଧିକା ସ୍ପିଡ୍ ଅଛି ମାନେ ସ୍ପିଡ୍ ଆସିବ ଅଧିକା ସ୍ପିଡ୍ ଚାଲିବ ନା
Please mute yourself. Hello. Hello. Whoever is speaking, please mute yourself. So we were discussing the receiving end power. For the receiving end, you can find out the power, active and reactive power expression using the same method. So it will be the receiving end voltage phasor and the receiving end current phasor with conjugate. Okay. So this was VR minus delta and IR conjugate. So IR you will have to use this expression. From this equation you can find out what will be IR and you will have to replace here. And then if you simplify this, you will get the active and reactive powers. Fine. Now one interesting thing is if you remember, the sending and active power expression was also same. It was same 3 VSVR by ZC sin beta L sin delta. So this expression and this expression, they are same. Because we have assumed a lossless line, that's why there is no loss in between of active for the active power. So for lossless line, PS equal to PR. PS equal to PR for lossless line. However, the reactive power expression is not same. QS is not equal to QR. QR and QS, they are different. Okay. They are different. So that's what I have written here. PS is equal to PR, but QS is not equal to QR. Now I shall start the numerical problems. At any point, if you don't understand something or there is any doubt, please interrupt me and ask me. Okay. Yes, another thing that is we talked about the sending end and receiving end expressions, but what if we need to find out the reactive and active power at a particular point like this? So suppose there is a point x which is there is a point which is x kilometer distant from the receiving end like this. So how to find out that? That also you can find out uh, by using the expressions that we talked in the last class. Okay. So there first we found out generic expression at any point x, then we replaced x equal to 0 and x equal to L. When is x equal to 0 and when is x equal to L? So, so if you are defining the quantities from the sending end, so if the point is x distance away from the sending end, then x equal to 0 means the sending end parameters and x equal to L means the receiving end parameters. You can also do the vice versa. You can also take calculate from receiving end and then you can find out the expressions. Okay. So that point may be x distance away from the receiving end. Then what will be the expressions? Like it will be same only. Just that how you want to express it from the receiving end side or from the sending end side. Yes. Okay, so let's start the numericals. Just wait a minute. I will just come back. Just wait a minute. So today, whatever problems we will be discussing, that is one single problem. We will solve parts of it. Part by part, we will solve. The parameters will be applicable for all the questions. So a 400 kilovolt, 800 kilometer, 60 hertz, symmetrical lossless three-phase transmission line has these parameters. So transmission line, so just ignore this part. So 800 kilometers, 60 hertz, 400 kV. These are the parameters. Line inductance 0.8 millihenry per kilometer. Line capacitance is 12.1 nanofarad per kilometer. For the rated load condition, the power angle is given 60 degree. So the delta value is given here. Delta value is equal to 60 degree. Okay. Determine the line surge impedance. Yeah, sorry for the interruption. I got a call. Yeah, so we were discussing, so at the rated power condition, the power angle is given 60 degree, determine the line surge impedance. This we calculated in the last class also. So surge impedance is the characteristic impedance only, but we will consider the lossless condition. So this is equal to L by C. Okay, so this is L by C, root L by C. This is 0.8 by 12.1. This is millihenry. So it would be 10 power minus 3. And this is nanofarad. So this is 10 power minus 9. 10 power minus 9. Okay. So what is the answer? The answer is 257.129 ohm. That is the surge impedance in this case. Okay. So the correct answer here is option C. Fine. This is the first question. What is to determine the surge impedance loading of the line? Okay, that is the second question. So I am removing this. Can any of you tell me how to find out the surge impedance loading?
VR square by ZC.
Sorry, can you repeat?
VR square by ZC.
PR square by ZC, right? So what is anyways surge impedance loading? Basically, if this is your VS, this here, and this side you have VR, in the receiving end, the load, whatever load you are connecting, that is equal to your surge impedance that we just calculated. So there will be some load here. There will be some load. This load is equal to ZC. When this load is equal to ZC, we call it surge impedance loading. SIL. Right. So obviously, first of all, we already saw that when there is surge impedance loading, the voltage profile is flat throughout the transmission line. It doesn't change at all. It is independent of the distance. No matter how long is the transmission line, the voltage will remain same throughout the transmission line. So Vs equal to VR, and your SIL value would be VR square by ZC. This is PR square by ZC. Okay. Now remember one thing. So if you take line to line voltage, then this is the expression. But if you take in terms of phase quantities, phase voltages, if you take, then you will have to multiply 3. If you take line to line voltages, then this is the expression. So it was 400 kV and it was a line to line voltage. Whenever you see any question, unless it is specifically mentioned, whatever is mentioned in the question, that will be line to line voltage, not phase voltage. Okay, remember that. So this is 257 that we calculated in the first question. And its unit will be in megawatt because 400 kV, the voltage is 400 kV and we are having the square. So the unit is in megawatt. Okay. Now tell me what is the value?
$622.25.
Okay, 622. Okay, the 0.25. Okay, like uh, so let's see here. Yes, we have option B as 622. So option B is the correct answer. Okay, let's go to the next question. So what they are asking, determine the phase constant in degree. This also we did in the last session. But anyway, and remember all these questions we are having this data. This 400 kV, 800 kilometer length, 60 hertz. So this data is common for all the questions, whatever questions we are discussing today. Now we need to find out what is phase constant. Okay. Is the phase constant means the quantity beta. That is we call as phase constant. Beta is called the phase constant. Now already they have mentioned the line is lossless. So if we just find out beta, beta is what? beta is x and we discussed this in the last lecture, last tutorial session. Okay. So X is the inductance, inductive reactance, and B is the capacitive reactance. So that would be omega L multiplied by omega C, and omega will come out of the square root, and this will be LC. What is omega? Omega is 2 pi 60 because the frequency they have given 60 hertz. So this also you take care whether they have given 50 hertz or 60 hertz. And LC value, it was also given 0.8 millihenry, 0.8 millihenry and 12.1 nanofarad. Right, nanofarad. So can you calculate this and find the answer? Please, can any of you please calculate this? What will be this quantity?
1.172 into 10 power minus 3.
1.17 into 10 power minus 3. Yeah. But remember the unit of beta is radian per kilometer. This is radian per kilometer. Okay. So for finding out the angle in radian, you will have to multiply it with the length. The length is 800 kilometer. So just just multiply this with 800. Okay. So if we multiply this with 800, it is 0.936. 0.936 radian. 936 radian. And if we want to find out this value in degree, what will be the value? Can you please calculate in degree? What is the value in degree? Beta L? So this value comes out 53.62 degree. Here the closest option is 53.77. So option D is the correct one. Then determine the rated load of the line in megawatt. We will have to find out what is the rated load of the line in megawatt. So how should we proceed? Can anyone give me any hint how to proceed for this one? Rated load. Rated power, rated active power basically. Rated load. Tell. You are not audible.
We multiply the surge incidence load with the ratio of sine lambda upon sine beta L.
Just a second. I will just mute myself. Maybe there is some.
SIL multiplied with sine lambda upon sine beta L.
Yeah. So first of all, before solving any question, just see what they have what are the properties they have mentioned. So if they have mentioned it is lossless, then you can straight away find it. So lossless they have mentioned, right? The line is lossless. So the sending end power and receiving end active power will be same. And the expression we already saw. What was the expression? VS, VR, VS, VR, then by ZC sine beta L, sine beta L, and here there will be sine delta. What is delta? Delta is the power angle. Now here you will have to take line to line values because I haven't added the 3. Otherwise, if these are the phase quantities, then there would be a 3. As they already have given us the line to line quantity, they have given 400 kV is the voltage, and this is obviously the line to line quantity. So we can directly take this. Okay. So in the numerator, we have 400 square. And another thing is, I have taken VS is equal to VR. Why? Because if we just go to they have also mentioned another thing, symmetrical. This they have mentioned. What is a symmetrical line? So for symmetrical line, PS is equal to VR. Okay. PS is equal to VR for symmetrical line. In between the voltage may vary. In between there the voltage may be higher than the say higher than VS or lower than VS. But at the sending end and the receiving end, these voltages will be equal. Okay. So that's why I have taken 400 square. ZC we found out already, which was 257. And beta L, the angle beta L also we found out which was sine 53.77 degree. And what will be delta? In the question, first question, they mentioned that for rated condition, you take power angle equal to 60 degree. In the first question, it was mentioned. So we will take sine 60 degree. So you can understand if this power angle changes, if delta changes, then the power will also change. The active power will change, and the maximum power transfer will happen when delta is 90 degree, because that's when the sine delta will be unity and we will have the maximum power transfer. So as delta increases, P also increases. P also increases. Now can you calculate this? Sine 53.
Around 669.36 megawatts.
669. Okay. 669 megawatt. So do we have 669 here? Yeah. So option B, 668. So close enough. That would be the rated load of the line in megawatt. Okay, now question number 5. Determine the reactive power at the receiving end considering symmetric line at no load condition. So what are the conditions? First of all, no load condition means there is no active power is flowing. There is no active power. That's the no load condition. And the line is symmetric again. So you can take Vs equal to Vr. What will be the reactive power at the receiving end? For no load condition, for question 5, no load condition, Ps equal to Pr equal to 0. Okay, that is the no load condition. So whenever Ps equal to Pr equals to 0, so just now I told you that along with power angle, this active power varies. Whenever power angle is 90 degree, we have the maximum power transfer. And when this active power is 0 at no load condition, then delta equal to 0. That we can take. So that we can infer that when at no load condition, this power angle is equal to 0. Okay. Now, what will be the QR? The reactive power at the receiving end, that is PS PR cos beta L minus VR square cos delta divided by let's see sin beta L. Okay, let me just verify whether I have written the correct expression. VSVR cos delta minus, sorry, I have, this is cos beta L. So here I have, this is wrong. This is cos delta and this is cos beta L. Okay, this is cos beta L. Now we know all these things. Delta equal to 0. Beta L we already found out. Beta L we already found out 53.77. 77. ZC also we know. And BSVR is again because they mentioned the line is symmetrical. So VR and VS value will be equal to line to, this is line to line voltage 400 kV. This is 400 kV. Okay. So now if we find out, so now please calculate and tell me what will be QR. Yeah. Can you, are any of you calculating this value? Just replace the numbers VR, VS and VR. This is so the 400 square will be the common. It would, inside it will be cos delta minus cos beta L, and in the denominator ZC sin beta L. Hello, are you there?
Yes, ma'am. It's around 315 megawatts.
315. You told 315, right?
Oh, yes.
Yeah, but it will be not megawatt, it will be megavar because this is reactive power. So this is
Sorry.
megavar.
MVA. Okay, sorry.
Yeah. Okay. So question number 5. 5. Yeah. So option B, 315 megabar. This is the right answer. So these questions are actually pretty simple to solve. If you just correctly remember the expressions, or if you don't also remember, you can quickly derive them. Okay, they are not, so you can derive them. And like and there are some tricks also. You can just, like they are not very difficult. And most of the time, if they give this is a symmetrical line, then V is equal to VR. So this will be V square here and here. And here it is cos delta minus cos beta L by ZC sin beta L. So if you just know the expression correctly, the answer you can solve it. There is no complication. The next question, determine the reactive power at 400 kilometer from the sending end, considering symmetric operation of the line and rated load. Again, they have used the term symmetric operation. So the line is symmetrical, Vs is equal to VR, and at rated load, what will be the reactive power at 400 kilometer from the sending end? If you have seen the lecture, you should be able to answer it. Can any of you answer it? What would be the reactive power at 400 kilometer from the sending end? Okay, so I will tell you. Whenever we talk about symmetric line, in that case, when we were discussing the expressions, if you remember, we saw that PS and PR, the active power expressions, if you see, what was the expression? PS, PR, PS, PR by ZC sin beta L, and this is sin delta. If you see this expression, there nowhere you can get any x. Can you see here x? X can be any point in the from sending end to receiving end. Okay, it is independent of the length of the distance, the length, because there is no x here. From starting from the sending end towards the receiving end, if this is the lossless line, then whatever active power starts flowing here, the same power will reach here. Okay, so if you are sending a power of PS from this point, you will get the same power here at the receiving end. Okay, so whatever be the length, it doesn't matter. What the power you are sending here, you will get here the same power. Okay, so this is for active power, but the case is not the same for reactive power. The reactive power is a bit different. If you see this expression over here, so if you see this expression over here, this px can be the active power at any point. From here to here, you can choose any point. So this will be the expression for a lossless line. But for qx, this is dependent on x. If x changes, the value of qx will also change, right? So this is dependent on this x value, right? So if starting from here, x will change and q will also change. Now see the question, at properly. If you just see here, the question we were discussing, they have asked at 400 kilometer from the sending end. They have asked from 400 kilometer. So the line length was given 800 kilometer, and we need to find out the reactive power at 400 kilometer from sending end. So this is exactly the midpoint of the transmission line. This is exactly the midpoint. Okay. This is exactly the midpoint. Now in this expression, in the expression of qx, if you replace x by L by 2, because this is the midpoint, so x is equal to L by 2. If you replace this, then you will get qx is equal to 0. Let's see one by one. So this is beta L, this will be beta L by 2. So overall it will be beta L, right? So this is sin beta L. This is sin beta L. And what will be this? This is beta L minus 2 beta x. So again L by 2. So this is beta L minus beta L, sin 0. So this term becomes 0. And this is again L by 2. So sin beta L. Here also we have V square sin beta L. Here you have VR square sin beta L. And for a symmetric line, Vs is equal to VR. So this quantity becomes 0. If you know this, you don't have to calculate anything. You can straight away put 0. You don't have to calculate. If you know. Okay. So this will be 0 MVAR. There is no reactive power at 400 kilometer. Now the next question. Determine the active power in per unit from 250 kilometer of the receiving end side when load angle is 30 degree. They have asked to find out the active power in per unit. So any of you know what is per unit? Have you read about this term per unit? Per unit quantity is actual value by base value. Actual by base. This is what we call per unit. What is base? Base we can take anything. Usually the base is taken as the rated power. Is taken at the rated power, but this is not a strict condition. You can take your base power anything, okay? And you will represent the actual power in terms of the base power. Then it becomes the per unit power, okay? So rated power. It is a normalized quantity. It will be in between 0 and 1, okay? So it will be in between 0, not necessarily, it can also be greater than 1 based on what you are taking as base. So if you take the maximum possible power as the base, then it will be less than 1 always. Otherwise, it can also be greater than 1. Here they have mentioned consider SIL as the base load. Means we will have to take surge impedance load as the base load. Right? Let's then solve it. As we are talking about active power, it doesn't matter at which distance they are asking. It could be 250 kilometer, it could be 400 kilometer, it could be 500 kilometer, doesn't matter. Because active power doesn't get affected with the distance. Okay. So we don't have to worry about the X here. This information is not required here. This is just an extra information. We don't need it here. Because active power, in active power expression, we don't need to put the L value, X value. Okay. So the same expression that we used earlier, PS or PR, the same thing. This is PS, PR by ZC sine beta L times sine delta. And the delta is specified 30 degree. Here they have mentioned delta equal to 30 degree. Okay. So you can find out PS, and then what you will do is your per unit active power would be your this calculated value PS calculated divided by the SIL. SIL we already calculated. And you can also do another thing that will be so that will take even lesser time. These VS, VR, all these things are same, right? ZC, the characteristic impedance is same, sine beta is also same. So we know that we can tell your active power is proportional to sine delta, right? This is proportional to sine delta. And when there is surge impedance loading, at that time delta becomes delta equal to beta L, okay? Delta is equal to beta L during surge impedance loading. So if you just divide them, all these things gets cancelled. So your per unit power you can calculate easily by this. This is sine delta, that is sine 30 degree in this case, by sine beta L. Beta L we already know what is beta L. In this way also you can calculate, or another one is you calculate this whole thing and then you divide it by the SIL. Okay. So sine 30 degree by sine beta L. Beta L equal to 53.77 degree. So sine 30 divided by sine 53.77. This comes out to be 0.6198. 0.6198. Okay. So option D is the correct option. Did you understand how to calculate this? If you have any question, you can ask. Okay. Let's proceed to the next one. Determine the value of the power angle when the line is loaded with SIL. We just discussed that when there is surge impedance loading, the delta angle is equal to the beta L. Okay. So the option D is correct. I will just show you this. This derivation is very small. So how this is coming? During surge impedance, we saw the power was VR square by ZC, right? And it will be equal to, because this expression we can always use. So this is VR, VS VR. This is the generic expression ZC sine beta L, sine beta L and sine delta. For symmetric line, VS is equal to VR. VS is equal to VR for symmetric line. So this will cancel this and this. ZC will also cancel. So from here we get sine delta equal to sine beta L during SIL. So the power angle during surge impedance loading is equal to beta L. Okay. So this is option D. Now let's discuss option question 9. Determine the reactive power in per unit at the sending end side when load angle is 45 degree. Again, consider SIL as the base load. So the per unit reactive power in at the sending end side when the load angle is 45 degree. You can think about it a little bit. This is also very easy. I will just get back to you after 7 minutes. Okay. So just think about it and try to solve it by your own. If you find the answer, tell me. Yeah. So do you
Option
we
D, minus 0.144.
okay. Okay. So how did you solve?
Using US formula and then dividing it by after getting QS, dividing it by using SIL value.
Yeah. So for the sending end reactive power, the expression is P square cos beta L minus VS cos delta by ZC sin beta L. That would be QS. You will have to find out the value. Okay. So if I just replace these values, cos beta L would be cos 53.77 minus cos delta is just, so they have, I think, given load angle 45 degree they have given. So cos 45 into 400 square divided by ZC 257 to sine. So this is QS is coming minus 89.58 megawatt, and then you will have to just divide it by the SIL because that is the base power. So QS by SIL, if you do, you will get the per unit reactive power. So this divided by 622.25. So that is minus 0.1439. So what you did was correct. Minus 0.144. This is the correct answer. Now the 10th question. Determine the reactive power at 200 km from the receiving end, considering a symmetric operation of line and no load condition. So they have given two things, again symmetric operation. So Vs is equal to Vr, and no load condition, that means delta is equal to 0 degree. Okay. Now we have this big bulky expression over here that we need to use for this. Yeah, so we need to use this expression. Okay, this expression for Qx. And they have given 200 km from the receiving end, the distance. But if you remember, so all this expression has been calculated taking the reference over here. So this x distance is from the sending end. So as the length is 800 kilometer, from sending end the distance would be 600 kilometer, right? So everywhere in the you have to substitute the x value by 600 kilometer, and then you will have to find out what is the qx. Okay. I will just see. I Control V. So now can you calculate this and tell me? The only thing you need to take care is the x value. They have given 200 kilometer from the from the receiving end. But if you take 200 kilometer and replace instead of x, if you put 200, then you will not get the correct answer, because this expression has been derived taking from starting from the sending end. So x is 800 minus 200, that is 600. So just replace x by 600, and then the rest of the things we already know. The beta value L is 800. L is 800. And ZC, all these things we already know. And yeah, so VS and VR, they are equal because the line is symmetric. Here there is 3 outside, so you can just take the 3 inside and make them line to line voltages. Then it would be, the 3 will not be here, it will be V squared sine 2 beta L minus beta x. Here also they will be all line to line quantities. Here beta x comes out to be, so beta was 0.936 radian. If I remember correctly, it was 0.936 times 600. It will be, sorry, beta, no, beta was 1.17, sorry, radian per kilometer, 1.17, 10 power minus 3, and let's multiply it with 600. 1.17 into 8 minus 3 into 600. So this is 0.702 radian. You can convert it to degree if you wish, or you can also calculate everything with radian. But just stick to one thing, either radian or degree, don't mix it up. This is 40.22 degree. So this is beta x. Or just you can directly do L minus x. L minus x will be 200. So beta into 200 for this angle. Beta into 200. And here also it will be beta times L minus 2x. But directly also you can find out, that would be quicker.
Ma'am, what should be the power angle delta we need to take here? I think main in the
Here-
question delta
Here they
cos
have, here they
60
have
degrees.
mentioned. No, see here they have mentioned no load condition.
Delta
Okay, I will do the calculations. Let's see. 400 square. This we can take out of the bracket because it is everywhere. Beta times L minus X. Okay, so this is sine. This is sine 26.81 degree. The first one. Then 2. This is cos delta. So delta is 0. This is 1. Sine. This is beta minus 2x. L minus 2x. So into this is plus because some minus term comes in the sine angle. So minus and minus becomes plus. This is the same 26.81 degree. Then minus 2 beta x. This is sine 80.44. So this is sine 80.4 degree. 80.4 degree. This is the numerator. And in the denominator, 2 into 257 multiplied by sine square beta n. This is 0.65. This 3 sine 26.81 minus sine 80.4 into 400 square divided by 2 into 257 into 0.65. So this is coming 175.8. Did you get the same answer? Did you get this answer?
Approximately same, around 180 or 40.
Okay, okay. Okay, so option D, that is the best match here. That will be the correct answer. Okay, so there are no more questions. If you have any question, any doubt, you may ask on today's discussion. You are seeing the lecture videos, right? Or you are not seeing?
But yes, I'm watching the lecture. And can you explain the sixth question answer and the
Which question?
sixth
Which
question?
question?
Question number
Six.
6.
Question number 6. Okay. Question number 6. So determine the reactive power at 400 kilometer. Okay. So basically the expression we just used, Okay, here, over here, this expression for reactive power, this expression is valid for any x. So you can find out the sending and reactive power if you put x equal to 0 in this expression. Then you will found exactly the expression that we used for sending end. If you put here x equal to L, that means the total transmission line we are covering. If you put instead of x, you put here L, we put L, and then you will get the expression for the receiving end reactive power. Okay, this is the generalized expression. Now they have asked the question that you find out the reactive power at x equal to 400 kilometer. X equal to 400 kilometer. And the line length here they have given 800 kilometers. So this point is exactly in the mid portion of the line. Okay. So if we go by the equation, if you put x equal to L by 2 here, you will see that qx comes out to be 0. Okay. So this is a property. Okay. So qx comes out to be 0 no matter what is the length of the transmission line. At the midpoint of the transmission line, the reactive power will be 0. Okay. For that, you don't need to calculate this. Right. Now, why does this happen? For a symmetric line. So if you just plot it, if in the x-axis, if you plot, this is x, and here you have q. Q varies like this. Okay. So q varies like this. This is minus q. This is plus q. Another thing is for symmetric line, you will see qs is equal to minus qr. Their magnitudes are same, just that they are 180 degree apart. There is a negative sign. Okay, for symmetric line I am talking about. And the curve comes something like this. In the lecture also, sir has explained that. So this is the midpoint. This is basically 0 point. This is L. This is L, and this is x equal to L by 2. So at this point, you will always get the reactive power is 0. Okay. And if you also calculate it, putting x equal to L by 2, then also you will get q comes out to be 0. Okay. Did you understand why the answer is 0?
Yes, I got it.
Okay. Okay. So any other question? So if you don't have any other question, then we can wrap up today's session. So are you guys like master students or bachelor students?
I am master student.
Okay. So in bachelors, you have are you from electrical background or any other stream?
Electrical background.
Okay, so you must have studied then basic power systems. In there also these things were there. If I
Yes,
the basic power yeah.
Yes, power flow analysis.
Yeah. Okay, so thank you for attending. We can conclude today. We will meet in the next week. Okay. Thank you.